Good morning everyone. We are from Group J and today we will be presenting about phase lock loop or PLL for our subject DELE1213 or better known analog electronics. Our lecturer for the subject is Dr. Noor Azlina Binti Bahari. Introduction. Let's start with a quick introduction. A phase lock loop or PLL is basically a control system that keeps a signal in sync. It does it by matching the frequency and phase of the circuit called a VCO or better known voltage control oscillator to a reference signal. PLLs are super important in electronics. They are both used analog and digital system to keep signal stable, accurate and always synchronized. You can find PLLs in devices like phones, radios and even computers. Make sure everything runs on right timing.
Now let's look at three main components that make up a phase loop. First, we have the phase detector, which is compare the phase of the input signal and the output signal. Second, there's the low pass filter or LPF, which remove unwanted noise from the error signal. And lastly, the voltage control oscillator or VCO, which changes its frequency based on the filter signal. These three parts work together to form the feedback system. Here's how they work together. The phase detector checks if the input and output signal are in sync. If they are not, it creates an error signal. The signal passes through the low pass filter to make it smooth and clean. Then the VCO uses that signal to adjust its frequency. This loop continues until both the input and output signal match in phase and frequency. And when that happens, we say the PLL is locked.
Okay, now let's look at the operation phases. A phase lock loop goes through the three main phases during operation. First is the startup or unlock state. At this point, the output of the VCO is not yet synchronized with the input signal. Next is the acquisition phase, where the PLL starts adjusting itself. It compares the input and output signals and slowly makes changes to get them aligned. Finally, once everything is matched, we enter the lock state. In this condition, the PLL keeps tracking the input signal and stays locked even if the input changes slightly. This phase is stable and accurate. And then let's understand how this works in real time. When the circuit powers on, the VCO starts off unsynchronized. The phase detector immediately compares the VCO output with the reference input and produces an error signal. This signal goes through the low pass filter, which removes any noise, giving us a clean control voltage. The VCO uses this control voltage to adjust its frequency, either increasing or decreasing it to reduce the difference. Eventually, when the output is close enough to the input in both phase and frequency, the PLL becomes locked. Even after locking, the loop stays active, constantly adjusting and maintaining the lock, especially if the input signal changes a little bit.
In slide 7, we explore the important formula and parameter used in analyzing a phase lock loop system. Three critical performance parameters are loop bandwidth, capture range, and lock range. This defines how fast and accurately the PLL can lock onto an input signal and how stable it remains during operation. For the first key component is the phase detector, which compares the phase of the input signal with the output of the VCO. Its output is a voltage proportional to the phase difference. The formula is VPD equal to KPD multiple to phase difference, where is the KPD is the gain of the phase detector in volt per radian and phase detector. Next, this voltage phase through a low pass filter, which smooth out high frequency component. A simple first order low pass filter has the transfer function. The formula is HS equal to 1/1 plus SRC, where R and C are the resistance and capacitance value and S is the Laplace variable. This filter helps to remove noise and provide a clean control voltage for the VCO. Next, the filter signal then control the voltage control oscillator, which adjusts its output frequency based on the input voltage. Its formula is F VCO equal F naught plus K VCO multiple V in, where F naught is the free running frequency of the VCO, K VCO is the VCO gain in Hertz per volt, and V in is the input control voltage. These three formulas, PD, phase difference, low pass filter and VCO work together in the feedback loop to help the PLL lock onto the desired signal. A good understanding of this equation and parameter help in designing stable and responsive PLL system.
PLLs are used in so many level electronics. For example, they are used in frequency synthesizers to generate multiple frequencies from a single source, and in clock generation to keep systems like computers in sync. They also help in FM demodulation, meter speed control, and DTMF decoding, which is how phones detect keypad tones. Basically, anywhere timing or frequency accuracy matters, you will find PLLs doing the job. Now, let's look at where PLLs are used in real life. In mobile phones, PLLs help switch between network frequencies so we can make calls and use data smoothly. In radios and TVs, they allow us to tune into different channels accurately without any distortion. In computers and digital systems, they keep the internal clock running at the right speed, making sure data is processed correctly. Now, PLLs are also used in robotics and industrial machines, especially to control motor speeds and keep things precise and synchronized. To wrap things up, phase lock loops are small but powerful systems used across many industries. They are essential for keeping signals synchronized, clean and stable. From a simple tone decoding in phones to complex clock management in processors, PLLs are everywhere. They work silently in the background, but without them, many of our modern electronics simply wouldn't function properly. So even though the concept may be technical at first, understanding PLLs gives us a deeper appreciation for how electronics stay in sync. The end.